Hello, good afternoon. So now let's proceed with our first talk of this afternoon. Oh, our only talk of this afternoon. So it's a pleasure to have here Letícia Mattos from Heidelberg. So thanks, Letícia.
Thank you very much for the invitation. Thank you very much, you all, for being here. I'm very happy to be here. I'm going to talk about Prague dimension of sparse random graphs. This is a joint work with Felix Joos from Heidelberg University. Before we define Prague dimension, we need to define what is a product between graphs. So given some sequence of graphs, say G1 up to Gk, we define the product of them as the graph with vertex set given by k tuples, where the first entry is, say, a vertex of G1, the second entry is the vertex of G2, and until the kth entry, which is a vertex of Gk. And we connect two tuples, say x1 up to xk to y1 up to yk, if the corresponding I entries form an edge in the Gi graph, right? So you must have Gi, yi, an edge for every single I from 1 up to k. Is this definition clear? Yeah? Okay, so I also have an example. So how many vertices does this product have? 6, good. So let's put these vertices there. So the vertices are 1a, 2a, 3a, and so on. And then we have to connect 1a to 2b and 3b, 2a to 1b and 3b, and so on and so forth, right? And you can actually check that this example gives us a 6 cycle. So one of the most important theorems involving products of graphs is this one in the 70s by Nesetro and Rodel, which states that if you were given a graph G, you can always find some large enough product of cliques so that this G is an induced graph of this product, okay? And well, this theorem might seem a little bit random, but they had some motivation coming from the induced Ramsey theorem. They wanted to show an induced Ramsey theorem, and they show that they show this theorem, and that it suffices to prove the induced Ramsey theorem for products of cliques. And here G is an induced subgraph of these products of some cliques. Is it clear? Yeah? And I remind you, what is an induced subgraph? G is an induced subgraph of a graph H if you can find some subset U of the vertex set of H so that G is isomorphic to H restricted to this subset of vertices. Okay? Okay, so now we can define the Prague dimension. The Prague dimension of a graph G is the minimum S so that you can find G as an induced subgraph of the product of S cliques, okay? And this is sometimes regarded as some measure of complexity of your graph. And they also had some motivation coming from dimension of pole sets. So people studied what is the dimension of pole sets, which is the minimum number of chains you need to take to recover so that the intersection of them recover your pole set. And yeah, so this parameter is regarded as some measure of complexity. Okay, so let's come back to our example. What would then be the Prague dimension of the 6 cycle? 2, right? Because C6 is not an induced graph of any clique, and we just wrote as a product of 2. So the Prague dimension of C6 is 2. Good. But as you can see, dealing with this parameter, it seems a little bit hard, right? So you have to check many products of cliques, and how do you show that the graph you want is an induced subgraph of this product of cliques? This seems a little too hard. So instead of working with this parameter, which is the Prague dimension, we work with something called IDIM, so I dimension. let me just say that why this name is Prague dimension. Well, because these people from the previous theorem, they are Czech. And when in the paper, it says that, well, the paper was sent from Prague. So this is why. Mathematics are very creative. OK, so let's talk about something which is much simpler to understand, which is this IDIM. What is this IDIM parameter? For a graph G, IDIM is the minimum k so that you can write the complement of G as a union of k subgraphs. But these subgraphs, they must have a determined shape, which is they are vertex disjoint union of cliques. Okay? So you want to cover the complement of G with unions of vertex disjoint cliques, right? And Nesetter and Rodel, they showed in the 70s that for every graph G, these two parameters, the Prague dimension and the IDIM, they differ by a factor of 1. So from now on, we are essentially only going to talk about this IDIM parameter, OK? Right. So unfortunately, understanding this for every single graph, it's pretty hard. So Nesetter and Polterl, they showed in the 70s that the problem of determining whether the Prague dimension is at most k is an NP-complete problem. So it is essentially hopeless to solve this for every graph. And because of this, it's natural to come up with some questions that we have some hope of answering, right? So I'm going to list 3 of them. The first one is, what is the max IDIM over all graphs on n vertices? The second one is essentially the same, but we put a degree restriction. So what is the maximum IDIM restricted to graphs on n vertices with max degree delta? And finally, what is the asymptotic behavior of this IDIM when G is a random graph? All right? Yeah?
So the definition of IDIM is, can you just go through it again?
Yeah, sure. Thank you very much. Yeah, is this one. For a graph G, IDIM is the minimum k so that you can cover the complement of G with vertex disjoint unions of cliques.
So for instance, for C6, you can cover the complement of C6 with like 2?
Probably yes.
Okay.
I mean, they differ by ones, right? So it would be 2 or 3. I am not sure. Yeah. Is it clear? So, and I also like to say this in terms of actually we are covering the known edges with independent set factors, right? So we are also going to use this name. So we are going to cover the edges with independent set factors.
Well, for C6, so you have these 2 cliques and the matching.
Ah, right.
So that's 2.
Yeah, exactly. Thank you very much. Yeah, so it's 2. Is it clear?
We didn't hear it.
The C6 you can cover with 2 cliques and a matching. So it's 2. Yeah? Good? Everybody's happy? Yeah? OK. So let's, oh no, let's guess. Pretend that you didn't see anything. What would be, I don't know, some silly bound you can have on the IDIM on any graph on n vertices? N over 2, why?
The complement of a matching.
Ah, so you want to take matchings, right?
Yeah.
Right. This n over 2 is not exactly the answer, but taking matchings is a good idea. But first, let me briefly mention another silly bound, which is just going to be given by known edges, right? So each factor, you can take each factor as a known edge. So and you have the number of edges in the complement, so a silly bound of this is just the number of edges in the complement. Is this clear? Yeah? And the other approach will be given by what you said. Instead of taking each edge individually, let's just take matchings, right? But if we take matchings, this minimum number of matchings that you need to cover all the edges of the complement is a definition of something that we know already, which is the chromatic index of a graph, right? The chromatic index is just the minimum number of colors that you need to cover the edges of your graph so that you don't have a monochromatic cherry. So this is also an upper bound on this IDIM. Is it clear? Good. Right. And this can be, say, at most n. Let's just give this silly bound. Is this sharp? Can someone give me some example which is close to n? Yeah?
Chromatic index or for IDIM?
For IDIM, sorry. Exactly, perfect. The complement of a star is just going to give you n minus 1, right? You take each known edge, and you need n minus 1. And this is exactly the truth. So this was shown by Lovas, Necetero, and Poultrol in the 80s, that for every large n, we have the maximum is exactly n minus 1, and the only extremal example is given by this star. So we are done with the first question. Let's go to the second one. What is the max IDIM for graphs on n vertices and max degree delta? Right, so for this, actually, let's try to understand some lower bound first in terms of some known parameters of G, okay? Let's write G complement as this union of HIs, where each HI is this vertex disjoint collection of cliques. And the best you can do with this vertex disjoint union of cliques, how many edges they can cover the most? Well, it is just the number of edges given by this factor where every clique has just size of the independence number of G. Okay? This is when you cover the most. And you have, say, n over alpha of them. So at the end, if we sum this up, we are going to have the number of edges of G complement is at most k times the number of edges of this collection of cliques, which is alpha choose 2 times n over alpha, which is at most k times alpha gn. And then this implies that we have this lower bound on IDIM. Okay? Is this clear? Yeah? Good. But now let's do a little bit of nonsense, but which is going to give some intuition of why we expect, what do we expect to be the truth. So first I remind you of this bound that the chromatic number of a graph G times the independence number is always at least n, right? And the chromatic number is at most, say, delta plus 1, so we can write this. So the independence number is at least n over delta plus 1. So essentially n over delta, right? Let's use, actually, let's pretend that this here is the truth, all right? Just to see what we expect in terms of the max degree. So if this here is the truth and your complement is a very dense graph, then this quantity here will be essentially n squared over n over delta times n, which gives us delta. Is it clear? Yes? Good. So surprisingly, this is not far from the truth. Ito and Rodel, they showed in the 90s that if your graph has n vertices, max degree delta, then IDIM is really at most delta log n. So this silly and wrong argument, it is correct up to a factor of log. And moreover, they show that this is almost sharp in the sense that they found a construction of a graph where the IDIM is at least delta log n over log delta plus log log n. And if I'm not mistaken, this is still an open problem to see, where exactly is the truth here? Can you come up with a better example or a better bound for this IDIM? Everything clear so far? Yeah? Right. So I want to show you now the proof of the upper bound of this theorem. And this is actually the only proof I'm going to show you today. It is very simple and very beautiful, so please let me know if you have any questions. And the rest is just going to be intuition on the problem. OK, so how do we show that we can cover the known edges of a graph with at most delta log n independent set factors, right? This is the question. What we do is the following. First, you take some random partition of the vertex set of your graph. And then we are going to use this random partition to create a collection of vertex disjoint independent sets, OK? So how do we do it? First of all, how do we choose this random partition? Right, so we have 300 delta log n partitions. All of them, they are independent from each other and random partitions. And for every single vertex, you place V in Vi, the part Vi, with probability 1 over delta. So for every vertex, you ask where it goes, and then you do that for every single vertex in your graph, and you have this 300 delta log n partitions. Is it clear? Right? OK. So, right. So now this random partition, you have this blob splitting the vertices. They don't form an independent set. All the parts, they don't form an independent set necessarily because you can have edges inside it. So what we have to do is just to delete these edges. And how we delete these edges? Well, you identify all the points, all the vertices in these edges, you take them, and you delete them. And now you have some new parts. Each of those are independent sets, OK? And now we just need to show that these new partitions given by these UITs, they cover the known edges with high probability. Is it clear? Good. OK, so let's start with something simpler. What is the probability that a known edge is covered by this sequence U of UITs? So fixed T, you have this collection of vertex disjoint independent sets, and you want to understand the probability that V is covered. So first, let's say U it goes to some part, say Vi, right? So I don't know which part it is. Let's say U is here. And for this edge to be covered, first of all, you need V to be in the same part, right? So this gives a factor of 1 over delta. So this is the factor of 1 over delta there. But for this to be still in UI, what we need is that all the neighbors of U and V, they must be outside Vi, right? Because at the moment they are inside Vi, you're going to delete U and V, or U or V. So the neighbors must be outside Vi, and they are outside Vi with probably 1 minus 1 over delta. And how many neighbors we have of U and V is at most 2 delta. So this is the 2 delta exponent there. OK? So this is a lower bound on the probability. Yeah, good? Right, so 1 minus 1 over delta to the delta is essentially E. So this, you have some lower bound of a constant times 1 over delta. And, well, this is the conclusion we have so far. Now, what is the probability that UV is not covered by any of these collections of vertex disjoint independent sets? Well, they are all independent of each other, so we just have to take the complement of the probability there in green and to the power the number of partitions we have. So this is 1 minus 1 over 100 delta to the 300 delta log n. And this is at most n to the minus 3. So we can just now make the union bound over all known edges, and the probability of a bad event happening is at most 1 over n to the minus 1, so we win. Okay? Good. So this is the proof. So it was quite cute, right? Okay. Nice. So now let's go then to the random graph setting. What is the asymptotic behavior of IDIM when G is a random graph? Let me just define to you which random graph model we are interested in. So we are interested in G and P, which is the so-called Erdős-Rényi random graph. The vertex set, let's say, is the numbers 1 up to n, and every single pair is present in this graph with probability P. So for every edge, you flip a coin, say a biased coin, its head with probability P, its tail with probability 1 minus P, and then every time you see a head, you put an edge, okay? So here, I flipped a coin for every pair, and this is what I got. So is it clear, the model? Yeah? Right, so let's come back to the bounds we got for the deterministic setting. For every graph on n vertices and say with a dense complement, we have that the number of edges of the complement is at most IDIM times the number of edges in the best clique factor we can get in the complement, which is just this partition into independent sets of size alpha. And right, so we had this bound. So this implies that IDIM is at least n over alpha of G. And this is also true for the random graph. We didn't use anything about the random graph yet, okay? And right, so what is alpha of G? What is the independence number of the random graph? This parameter is a well-known study parameter in combinatorics, and this theorem is due to this combination of works from Matula, Bolova, Erdős, and Fries. And essentially, it states that for P, which is much larger than 1 over n, but it's a little far away from 1, we have that the independence number is a constant times log NP over P. So this is quite well understood, and even a constant is known, but we don't need a constant here. So let's just plug in this into this silly bound, the silly lower bound. And this is what we got, right? So we have this regime of P, and by using the silly bound combined with this theorem on the size of the independence number, we have the IDIM is at least NP over some log. But on the other hand, this argument with a chromatic index gives an upper bound of n for this number, right? So we would like to understand where is the truth. So is it closer to n, or is it closer to this lower bound? And now let's think about P constant. So this, for P constant, this was first done by Guo, Patton, and Warnke 2 years ago. So they show that with high probability, the lower bound is the truth. Right. And this left open the sparse range of P. So from now on, we are mostly interested in P going to 0, okay? Is it clear? Yeah? Right, so very recently, there was this paper of Molnar, Rodel, Salles, and Schacht that showed for essentially any P you like, with high probability, you have that IDIM is at least this NP over log n times this log 1 over P. So it is essentially the trivial lower bound we got times this factor of log 1 over P. Okay, so they improved on that for random graphs. And they also showed that for every epsilon and P in between these two parameters, so first essentially n to the minus 1/3 and bounded by n to the minus epsilon, this Prague dimension and also the IDIM is a constant times NP. So essentially it's given by the degree of GNP, okay?
I'm confused about this versus the last slide. Like, because isn't there a log in the last slide? Or?
Which log?
Like in the previous slide.
Ah, right. So if P is polynomial, then the log cancels out. Yeah. Thank you. So the lower bound is NP. Any other questions? So the lower bound was already NP by their result, and they also showed the upper bound for this range. And you can see that you have a lower bound of n to the minus 1/3. It's not clear why this should be the case, why we couldn't extend this for every P, right? So, and this is what we did. So with Felix, we showed that for every epsilon and P in this range, which is almost the connectivity threshold, with high probability, we have that the Prague dimension is constant n times P. Is it clear? Yeah? Right. And we also showed a more general upper bound. So the previous theorem is actually a corollary of this one, where we could go until log n square over n. And yeah, we show that we have this expression, and then the logs, they cancel out if P is like something with a polynomial decay. All right? Okay, good. Now, let me first give you an idea of the proof of MRSS. What do they do? And what are the barriers in their proof? So they take K, which is essentially a constant times the independence number of GNP, and they take a pretty large collection of independent sets, okay? So, and they are chosen uniformly at random in GNP. And, okay, so what do we do to cover with these independent set factors? Well, we just gather all this I1 up to IT into buckets of size n over k. And then we take each of these buckets, and then we split these independent sets in a way that you have some independent sets which are vertex disjoint at the end, okay? So how do you split them? Well, you have this bucket with n over k independent sets. They are, say, here. You take, say, the first one. So this is I1. And to create a vertex disjoint independent set, the next vertex disjoint independent set, you just take I2 minus I1. And this is going to be my J2, say. And with J3 is just going to be I3 minus I1 minus I2, right? And this is also going to be a vertex disjoint from the rest, and so on and so forth. So this is how we create this collection of vertex disjoint independent sets, right?
Sorry, can you just remind us what is MRSS?
So it's Molnar, Rodel, Salles, and Schacht.
No, what's the theorem?
Sorry. Yeah. is this one. So yeah, thank you very much for asking. I want to show a proof idea of the upper bound of this theorem. So we want to show that n times p independent set factors suffices to just cover all the known edges. Yeah, thank you very much. Any more questions? And now everything is in terms of this k, but at the end we are going to recover this n times p bound. Right, so this is how we create this new collection. And by using this new collection of vertex disjoint independent sets, they show that this covers almost all known edges of the complement of G and P. Okay? And for the remaining ones, they had some tricks to cover it, and they also show that this is very little. I'm not going to get here into details, but what I wanted to show here is just the idea of how you cover a constant proportion of the edges. Okay? Right. So is it clear, more or less? Yeah? So in their proof, they had this natural barrier of n to the minus 1/2. Where this comes from? First of all, this collection of ji's, they cover a constant proportion of the pairs, right? So does the first collection we started with. So I1 up to IT, which is just this collection of independent sets chosen uniformly at random. Okay, so we must have that this should cover a constant proportion of the pairs. And okay, so how do you show that this collection covers a constant proportion of the pairs? Let's define some variables. The first one is xk, which is the number of independent k sets in G and P. And the other variables are the number of independent sets in G and P, which contains a given known edge, say UV. Okay, let's define these variables. So what is the probability that UV is contained in the first independent set which is chosen uniformly at random? It is just the ratio between these two variables, right? And how can you calculate this? Well, we don't have so many strategies. The only strategy essentially is just to say, well, we expect these variables to be concentrated around the expectation. And then we just say, right, if they are concentrated, then this is just the ratio between the expectations, and we can calculate this very easily. Okay? So if you have that xk is a constant times the expected number of independent k sets, then what we expect is this. So first of all, the expectation is n choose k times 1 minus p to the k choose 2. And well, the expression above, it is just the expectation of the number of independent sets of size k minus 2 in the common known neighborhood of these vertices. And on the bottom, I just have the expectation. Okay? Is this clear? I see less nods now. Yeah?
You don't expect this will be essentially cover all the known edges evenly, the size of the
Right, you expect to cover them evenly. Yeah, uh-huh.
Is that not easy way to that's the calculation?
But how do you show that you expect to cover them evenly? Yeah, but you're right, the intuition is correct. So evenly means k squared over n squared. Yeah, you can also, yeah, right. So yeah, you expect them to cover them evenly, and what this means is this probability you expect to be essentially k squared over n squared, which is, you can think of, this is essentially sampling a set of size k among n vertices, and then you want the two of them to be there, right? Yeah. Is it clear? Yeah? Okay. So again, we do this sort of same trick as the theorem of Nacetero and Rudel, So what is the probability that you don't cover this known edge if you take all these independent sets? It is just 1 minus k squared over n squared to the t. And then if you choose t large enough, meaning constant n squared over k squared times log n, then this event is going to be very unlikely to happen, and then we can take also the union bound. Okay? Right. So this is the conclusion, assuming that the expectation, assuming that xk is close to the expectation. Right? Good. And, well, why is this equal to, why does this give the Prague dimension of NP? It is just because you can gather those independent sets into buckets of size n over k, and you can check that this number is exactly n over k times np, okay? Just by the expression of the independence number. There's nothing happening here. And yeah, this will be true for p at least n to the minus 1 plus some epsilon, right? So far, nothing about the n to the minus 1/2 showed up, okay? Is it clear? Yeah? But now, now the barrier comes up, because when do we have that this xk, the number of independent k sets, is concentrated around the expectation? So in general, we expect that this variable will be concentrated around expectation plus or minus the square root of the variance. So in order to have xk, a constant times the expectation, we must have the variance at most the expectation of xk squared, okay? On the other hand, the variance is at least the expectation of the number of k-clicks, number of independent sets which intersect in exactly 2 points, right? And what is this expression equal to? First, you choose the first clique, which is you have n choose k choices. Then you choose the pair so that they are common. You have k choose 2. And then you choose the remaining vertices of the second clique, which is n minus k, choose k minus 2. And then you have times 1 minus p to the power the number of pairs you have in the union of the two, okay? And again, you can check that this is a constant times k to the 4 over n squared times the expectation squared, right? Okay. So what do we need here? What is a necessary condition? A necessary condition is that this number here, it must be at least a constant, right, for this to be true. So we must need p to the 4 n squared to be at least a constant, which translates into p at least 1 over square root n. So, and actually, if I'm not mistaken, this variable, xk, it's only concentrated in an interval of size constant times the expectation, exactly for p larger than n to the minus 1/2. So you have no hope of having this result for p smaller. So this is a barrier in their method, and how we overcome this barrier, instead of sampling the independent sets uniformly at random, you select vertex by vertex, uniformly at random. So let's define the process. So given your graph G and K, which is going to be a constant times the independence number, we sample an independent set as follows. You choose the first vertex uniformly at random. Then the second vertex, you choose uniformly at random among the known neighbors of the first vertex, and so on and so forth. So at some point, you're going to have some selection of V1 up to Vi minus 1, and then the vertex Vi, you selected in the common known neighborhoods of the vertices that you already chose. Okay? Is it clear? And the common known neighborhood, it is just the total vertex set minus the neighborhood of each of these V1 up to Vi minus 1 minus all the vertices that you already selected. Is it clear? Okay, good. But wait a second. Why isn't this the same as sampling uniformly at random, right? You are sampling each vertex uniformly at random, and why this isn't the same? So let me give you an example where this is not the same. So let K, say, is log n, and let G be this bipartite graph where in one part you have n over 3 vertices, and in the other part you have 2n over 3, okay? And I want to show to you what is the probability that UV is captured by a uniformly random independent set of size k. Let's first check what is this. So this is going to be, maybe I should ask more questions now. What is this going to be? What is the number of k sets, k independent sets of size k containing UV? In this graph. Yeah, exactly. So set of size k containing the first part. So it is just n over 3 minus 2, choose k minus 2. And then what is the number of, the total number of independent sets of size k? Well, you count in the first blob, and you also count in the second blob, right? So you just sum these two things up. And because k is very large, this expression here is dominated by the second binomial because of this 2. And then, oops, you essentially have this factor of 2 to the minus k coming from this 2 here. And then you have this k squared over n squared coming from the ratio between these two. OK? Right. But then, what is the probability that our random set, given by this independent set process, captures this non-edge UV? So how do we calculate that?
Just the first vertex needs to be in the correct block,
Yes.
and then afterwards you just need to, then everything's dependent after that.
Exactly. Yeah, exactly. So you just need the first vertex to be in the first blob. So this happens with a constant probability. And then you just have to capture U and V. So it's just k squared over n squared. So these two processes, they are really different. And you can see that the second process, it captures better, like it has you capture a non-edge more uniformly, right, if you do that. Any questions? Yep.
Is it possible that our random process breaks before we get the independent set?
Ah, right, it is. Yes, exactly. You can like keep sampling, and then at some point you, yeah, yeah, for sure.
But when does it work? It's like, which k do I have to choose for it to work?
I mean, you can choose any k and any n, and then if your process breaks, you are sad. Right? Yeah, then you have to sample again. How many minutes do I have?
I have
15?
15.
OK, good. Right. So what do we show then? We showed that for p in this range in between n to the minus epsilon and almost until the connectivity threshold, and for k, which is a constant times the independence number of G and P, the following holds with high probability. So for every single known edge of the complement of G and P, the probability that you capture a vertex is k over n, and the probability that you capture this known edge is k squared over n squared. So this always holds. And then we use this theorem to just build this collection of independent set factors given by the Prague dimension. OK? OK. Right. So let me mention briefly a second application of this theorem, which is also the number of cliques you need to cover the complement of GNP. So this is also a well-studied parameter in random graphs. And the usual notation for it is delta 1G. For a graph G, we let delta 1G to be the minimum number of cliques you need to cover the known edges of G, okay? And how the history of this parameter developed, first let me mention what we showed about this parameter. So for the first range of P given by our previous theorem, we showed that it is possible to cover the complement of G with n squared over k squared times log n cliques, because you just keep sampling these independent sets, and then you need this log factor just to take care of the union bound, to use the union bound, okay? Right, but we were not the first to study this, and yeah, maybe let me skip this. This was first studied by Bollebush, Erdős, Spencer, and West in '93. They showed that essentially the minimum number of cliques you need to cover the edges of GNP is n squared over log n squared, which will be the best if every edge is packed in exactly one of the cliques, right? But then they had an extra factor of log-log, okay? And right, so a couple of years later, Fries and Reed, they showed that this parameter is exactly what you expect in an almost perfect clique packing in GNP. So really, you have the number of edges over the number of edges of the maximum clique. And more recently, in the same paper of this Prague dimension, Guo, Patton, and Warnke, they showed that this θ1 parameter is the number of edges of GNP divided by the number of edges of a clique as well. So they also got essentially optimal result. For every P, which is in between 1 over n squared until almost very close to 1. So 1 minus epsilon, and epsilon is a constant. So this leaves the range where P is going to 1 open, right? If you think about it. So here we are talking about covering by cliques, but now how can we cover by cliques GNP where P it's close to 1? So in other words, we can think about, okay, let's cover the known edges of independent sets of sparse random graphs. Just rephrasing a little bit. Then for every constant epsilon and P in between essentially n to the minus 1/2 and n to the minus epsilon, we have that the number of independent sets which are needed to cover all the known edges of GNP is essentially n squared p squared log n over log np squared. So this is the number of edges of the complement of GNP over the size of the independence number squared times this factor of log n. So this here is saying that the factor of log n is really necessary. Okay? Yeah?
Is it constant depending on P or epsilon?
Here is right. It's depending on epsilon. Thank you very much. Yeah, for sure. Right. So here, let me show you what is the main idea of. So now I gave you the history of this parameter, and now I'm going to briefly show you the main idea behind why this independent set process, if you take an independent set given by this process, why this covers the known edges and the vertices uniformly, right? So let k be constant times the independence number, p in the range we are interested in. Let ik be the independent case set, which is generated by our process. And the question we are interested in now is, what is the probability that a given vertex is contained in this independent set given by this process? Okay? Well, actually, our final goal is to understand this probability for a given known edge to be contained in this independent set, but it is just simpler to analyze what is the probability that a given vertex is contained in this set. Okay? So is it clear what we are going to do now? Yeah? Right. So first of all, it suffices to show that for every j between 1 and k, the probability that the jth vertex is exactly equal to v is 1 over n. Okay? And then we sum this up, and then we recover the k over n. Right? Okay. So how do we show this? First of all, let's say that we have some t which is less than j. And then we already had the selection of v1 up to vt in our process. And let's say that we were successful so far, and then this v is contained in what I'm going to call the active graph, which is just the induced graph of g given by the common known neighborhoods of v1 up to vt. Okay? And well, v is here, and in the next step, we don't want to choose v, right? We want to choose a vertex which is not v, and we also don't want to choose a neighbor of v, because if we choose a neighbor of v, we are going to move it to it, which is going to create it plus 1, and we will have no hope of having vj equal to v, right? So this event, if we want this event to happen, then we must select a vertex which is not v and not a neighbor of v, okay? So let's pretend that this was the case. So we selected this u here. Then we select u, and then we move u to it plus 1. And in the next step, we then remove all the neighbors of u in the active graph, okay? So we have to remove all these neighbors here in the active graph. And as a consequence, the degree of v also gets updated, right? So the degree of v was 4, and now when we select u in the t plus 1 step, just becomes degree 2, right? And so you can see that for every step, in every step, this selection, if you don't want to select v in previous steps, these probabilities, they are depending on the current degree of v, right? So in other words, what we have is the probability that this vj is equal to v, this must be equal to, well, in the first step, you don't want to select the neighbor of v, and you also don't want to select v. So it will be this over n. Yeah, I should have also put v here, sorry, times the probability that you don't select a neighbor of v in the second step over the number of vertices you have in the current graph, and so on and so forth, until the last step, where you have to select precisely v. Okay? Is this clear? Yeah?
I'm worried about the expression not actually making sense.
Uh-huh.
Because the GT, like the GT is not deterministic, right?
Right.
And you're writing some deterministic number equals something.
Right, exactly. Yes, this is not correct at all. Like, yeah, this, it's like a typical outcome of this process, which selects v in the jth step. This roughly looks like this. So, yeah, I'm not saying that this is precise at all. This is just like the naive idea. Okay? But is it roughly clear? Okay, so, right. So to understand what this expression is equal to, we need to understand how these degrees, they develop along the process, right? So what do we expect to be the degree of V in the active graph GI, say? So you select the, say, T vertices so far, and then you have this active graph GT. And say you select the vertex U, then, well, roughly the degree of U should be P times the amount of vertices you have in the active graph, right? So this should be roughly P times V of GT. And what this means is that every of these ratios, they will give us essentially 1 minus P, okay? So you have 1 minus P given by all these ratios. We have J minus 1 of them. And then the last one, we have to see what do we expect for the size of the number of vertices in the active graph in the J step. And, well, when we select the vertex, we put it in IT, and then we also remove all the neighbors of it, right? So when we remove all the neighbors, the GT plus 1 is left with VGT minus the degree of this vertex U, which is roughly P times VGT. So in other words, the number of vertices in these active graphs, they are decaying by a factor of 1 minus P in every step. So we can just say that this expression, this whole expression is the previous ratios and times 1 over V of Gj, which is just this thing here. And then the 1 minus P to the J cancels out with 1 minus P, J minus 1. And you also have the factor of N. And this is essentially N. Okay? Yeah, more or less clear? Okay, so this is what we show. And, well, the cancellations, they don't turn out that simple because we have some error bounds in this known degrees, right? So we have to control how close these degrees are from the expected trajectory. And the formal theorem behind it is the following. So we define some error functions, f0 and fi, say. You don't need to care about what exactly these numbers are. I'm just putting here for completeness. And this theorem says the following. If we have some p in between these values and k, which is essentially the independence number, with high probability the following holds, this random greedy independent set process, we have that these degrees of v in gi, they are very close to their expected trajectories by 1 plus or minus this factor of fi, okay? And this is, it's true for every I, which is in the active graph gi, and I until k minus 1. And this also happens with a very high probability. So this is how we formalize the previous argument we had. Any questions so far? No? Okay, right, so I think my time is over, right? And so I thank you very much.